Hello, everyone. It's my pleasure to introduce what we are doing at the moment. We provide a reference implementation of zk virtual machine. And what actually makes this zk virtual machine special is that this zk virtual machine supports a very modern bytecode called WebAssembly. Okay, so I would like to give a very brief about what WebAssembly is and how it is used in the modern browser technology. So WebAssembly is an instruction set that are actually initially designed for running fast applications in the browser. But because actually its speed and architecture independent feature tracks a little bit more retention than browser applications, it becomes a very popular backend programming bytecodes as well these days. So this is the current WebAssembly landscape that people can use to build a WebAssembly ecosystems, both in Web 2 and Web 3. So, and in Web 2, the main container or runtime for running WebAssembly is called WASM Edge. And because WebAssembly is a native browser-supported bytecode in the browser, so you can write your WebAssembly code and then run in modern browsers with no obstacles. Okay. So inside the browser, we have a few use cases. I'm pretty sure that nowadays your everyday usage of browser application will use some kind of WebAssembly. And off-chain, off the browser, we can have RPC servers and server-side applications, hybrid native applications on mobile devices, many applications that are actually using the WebAssembly as their native bytecode. So what we do is we equip this WebAssembly bytecode with zero-knowledge proof. That means we have a WebAssembly virtual machine that not only provides the runtime of WebAssembly, but also generates a zero-knowledge proof. Let me give a very brief about what zero-knowledge proof is that the zero-knowledge proof actually can provide the execution of our application without redo the execution of the application again. So for example, if I want to actually convince you that I counting from 1 times 2 times 3 times 2 to the 32, and I would like to tell you that the answer of this large multiplication is start with number 1, 2, 3. It's very hard to convince you, right? Because if you want to get convinced, you would like to redo the calculation again. But the zero-knowledge proof is a magic that actually I can, without giving you the chance to redo the computation, I can give you a proof. After you check in the proof, you can believe me that the execution has been done correctly based on the specification, which is the long multiplication. So here, based on the idea of zero-knowledge proofs, we provide a WebAssembly execution VM so that every time you run the WebAssembly application in this VM, it generates a proof for you to prove that the result of the execution is somehow correct with no trust entity. Okay, and this is the TSC 2022 paper, which we provide a reference implementation in our WebAssembly prover. Okay, but all the previous stuff is not what I'm focusing today, right? What I'm focusing today is that I would like to integrate, at least provide an integration way so that every browser application can become a trustless Web3 applications. And how I do that? So let's review the classical architecture of a Web 2.5 game example. We can see that on the left-hand side, we have a game engine that mutates the game global state. Every transaction user sends to the game engine, the global state will change according to the gameplay logic, right? And every time we generate a new gameplay state, we can somehow synchronize that with the blockchain. That's called Web 2.5 state reporting on-chain, right? So what's the problem of this architecture is that there might be some human interference between the reporting process. Malicious software can somehow fake the new game global state and report the faked global state to the on-chain application so that your efforts that you put onto the game might get tricked in the on-chain data. Okay, so but it also has very good advantages of this architecture is because every time you change the game engine, you do not have to change your on-chain contract, the settlement contract, right? It has a separate line that it supports dynamic game update. So that means you can add more content to the game very frequently and very easily. Okay, so how to optimize the previous architecture? There's a naive and trivial ways to put everything on chain, right? Just imagine a shooting game. You shoot on your opponents, and before you know whether you shoot that or not, you sign your shoot first, and then you shoot the bullet, and the chain tells you that whether you have shoot your opponents or not, right? So the advantage of this architecture is that everything's on chain. You can hardly tweak the result, but the drawback is very obvious because every single activity you have to sign and have to wait. There's no much more FPS, no more FPS that you can play natively in your gaming machine, right? You have to interact with the on-chain contracts. Okay, so to balance this architecture and the previous architecture a little bit, you can actually doing a gaming architecture like this. There are a few games already using this architecture called Blade games, Mimi Disco, Automata, and the Zero X Pioneer. So I do not have a demo machine here, but if you're interested, you can come tomorrow. I will show you all these games and how these games using this architecture to do a fully on-chain game, but it's actually not fully on-chain. It's fully trustless off-chain. So the ingredients is that you, instead of running a game engine on the left-hand side standalone, we actually run that into a zkWASM virtual machine. So every time we submit the state changes from the left-hand side to the right-hand side, we not only submit the data change, we also submit the proof. So that means every time we want to update state, the on-chain verification contract will update the state according to the verification result. If the proof passes the verification, and if the updated data, the hash of the updated data actually is the correct witness in the proof witness, then we are going to update the proof and update the data. So you will see, because every time we doing a data update, we have to submit the proof. That means every time you change the gameplay logic, you have to change the on-chain contract to change the ping of the game image, right? So that makes you a little bit harder to change and upgrade your gameplay. But the benefit is that no one can tweak the result of the gameplay. And you do not have to sign your contract every time with on-chain verification, right? You can have a centralized game engine and sign the contract repeatedly in your browser so that you can play an FPS game and batch in the proof state changes and do the settlement every 5 or 10 minutes. Okay, so I will demonstrate this demo tomorrow in the workshop. And I'm going to talk about the last bit, which is the settlement. So, as we said before, the settlement only contains two parts. The first part is verify the proof. The proof is generated from the execution of a zkWASM VM. And we actually deposit the proof. It will do the state update and performs the settlement, which can be transfer, NFT minting, and maybe pull creating or define activities. Okay. And then, yeah, I will demonstrate that tomorrow. Okay. So now we have the trustless part. The remaining part for the engine that we have to do privacy. Right? Privacy is not very obvious once you have a zkVM. So the solution to actually adding privacy into a zkVM is somehow to add a zk verifier implemented in the zkWebAssembly VM so that it can do a client zk checker in the zkWebAssembly, which does not actually leaking any of the witness in the WebAssembly, and then verify the proof of the execution of the verifier. If anyone interested in that bit, it looks like this. We separate the execution proofs of the host circuit and the get circuit, and we put the trustless circuit on the host side. Okay. And at the end, we batch in the get proof and the host proof. You can find the GitHub under the Delphinus Lab Git repo, which contains the injection of the privacy of the zkWebAssembly VM. And for the last bit is if you do not have a powerful machine running the zkVM prover, you can using our online centralized zkWebAssembly prover cluster. It's pretty simple. You upload the WebAssembly you need and upload the input. It gives you the proof. That's the verifier part, sorry. That's an example, and I will demonstrate that example in tomorrow's workshop. Thanks. If anyone have questions, please ask me any questions. Thanks.